Chapter 3: Challenges and Solutions in Developing Optimized and High-Efficiency Optotronic Devices for LD Laser Diodes. So the topic overview for this chapter, I'm going to start off with the recap and also proceed with the challenges and solutions for developing the LD's best efficiency. The first one I'm going to touch is the 395 nitride-based laser diodes, followed with the GaN-based blue laser diodes, GaN-based green laser diodes, and VCSEL. So as a brief history, the first laser diode was demonstrated in 1962 by R.N. Hall. He observed a coherent infrared radiation from a forward bias from a gallium arsenide p-n junctions. In 1962, the same year, Holyoake Jr. demonstrated the first visible laser diodes, followed with a zinc selenide 2,4 group used for the fabrication of visible light emitting devices. 3-nitride crystal growth high brightness GaN-based blue LED and green LEDs was introduced by Shuji Nakamura from 1993 to 1995. Note that LDs needs precision current drivers in order to maintain a good lifetime. LDs often require an active cooling system called a TEC, which stands for thermoelectric cooler. Operating an LD at a temperature more than a specified level will unfortunately shorten the lifetime. It typically ranges from 10,000 hours to 30,000 hours. The peak wavelength of an LD is often tunable in the order of sub-nanometer by changing the operating temperature. The threshold currents and output power will also change with this temperature. So this is a typical characteristics of a qualitative of an LD showing an optical output power versus threshold forward current. So this is the spontaneous emission below the threshold current, and this is the point of threshold current, and the linear part is the stimulated emission lasing. Phosphor converted white light from LDs. The requirement for LDs for SSL is the ability to create the white light. Phosphor conversion schemes and material used in converted LEDs can also be used in LDs. There are three popular methods to create white lights. First one is the mixed direct emitters, all of the red, green and blue. The second one is the phosphors to fill in the visible spectrum, producing the white light. And the final one is the blue GaN LED plus yellow phosphor. LDs versus LEDs. LEDs coated and uncoated antifacets. It behaves like a mirror with a different reflectivities, which is an effective laser resonator. LEDs also benefits from the feedback and eventual gain of the stimulation emission of radiation. It has wide range of wavelengths, ranging from UV to IR, whereas LED is a spontaneous emission of radiation. The advantages of LD is the blue 3-nitride LEDs has a higher power conversion efficiency, or WPE, at a very high current density. It is much brighter than LEDs. The advantages for luminaire: this enables sizing that cannot be achieved with LED due to the direct emission of LEDs. The beam of light emitted from LED is more easily collected and focused compared to the LED's Lambert emission. The high radiance translates to the possibility of smaller area forces, and also it has a similar ability to create white light sources, which is excellent for color rendering. Disadvantages of LEDs, however, it has a shorter lifetimes compared to LEDs, and it has a lower peak efficiencies compared to LEDs, and it requires more processing and this translates to more expensive costs. 3,5-nitride-based laser diodes. Various systems were investigated for LEDs and LDs. The nitrides of aluminum, gallium, and indium proved to be the most effective. 3,5-nitride consists of GaN, InGaN, AlGaN, aluminum, gallium, indium nitride. Why? This materials reduces the energy consumption from 1 to 10 compared to the conventional light bulbs. It has high efficiency, long lifetime solid-state light sources, which is more than 10 to the power of 6 hours. It is almost forever. The reduced number of nuclear power plants worldwide by saving energy, and 3,5-nitride is not toxic to humans compared to the conventional 2,6 or 3,5 compound semiconductor materials. The 3-nitride material systems for LD's invisible spectrum. This covers a wide range of direct bandgap energies in the nitride 0.65 eV, gallium nitride 3.4 electron volts, and aluminum nitride 6.0 electron volt. The advantages for producing a gamut optoelectronics wavelength ranges from IR to the UV spectra. Commercial 3-nitride LDs grown by emulsivity on a C-plane 0001 wizard crystal by heteroepitaxy on sapphire or silicon carbon substrates. The devices on C-plane offers a very high performance, which has a very high dislocation densities 10 to the power of 9 cm squared induced by the non-native substrates. The 3-nitride wizard crystal is polar and piezoelectric, which is on the point of 6 mm symmetry. This is the word side crystal structure for C plane 0001, M plane 1100, A plane 1120, and semi-polar planes for all of the green and blue laser diodes. Blue in a spectral range of 430 to 470. In 1996, as Nakamura demonstrated the first blue LD with MQW based in GaN operating at a violet blue 417. The LD offered with 215 milliwatts of output power and a pulse current of 2.3 ampere. Researchers worldwide focused on the longer wavelengths towards a true blue or a royal blue, which is around 445 nanometer for digital displays and solid-state illumination purposes. In 2019, an LD was reported to operate at 445 nanometer with a continuous wave CW and output power of 1.17 watts, which is steady current under 1.0 ampere. Currently, a 445 LD PTTB 4050 with 1.4 watts of output power is commercially available from OSRAM. This is a structure of InGaN MQW LD. It is on a sapphire substrate, followed with a buffer layer of GaN and NGaN, and followed with a lot of layers including the InGaN MQW, and on top of it is the P electrode and also the N electrode. The applications of blue laser diodes. The first one is in the digital applications such as the high density optical storage including audio, video, data. Also for high resolution printing, high resolution lithography, and also full color projection displays. Second one is the light sources as the lighting, illumination, spotlight for the surgery, and automotive, airplane, or boat lighting. Also for the sensing and biomedical applications such as to diagnose cancer. The scientists at Oak Ridge TN National Laboratory, a blue laser diode based technique for locating the tumors in the intestinal tract by threading an endoscope into the patient's stomach or colon and shining a blue light. It is also to use as to detect chemical and biological weapons. cause certain otherwise invisible chemical and biological agents to fluorescence. Green laser diodes. In the green region, green LDs based on tier 6 compounds have first demonstrated in 1993. A tier 6 based laser diodes has poor reliability under the high drive current in lasing condition. Group 3 nitride materials has demonstrated they are promising for making reliable green LDs. Fabrication of GaN-based green LDs is more challenging compared to the blue and also ultraviolet LEDs. The peak gain of GaN-based LEDs decreases as the emission wavelength increases from violet to green range, which results into increasing threshold currents and decreasing the efficiency of green LEDs. Challenges on green LEDs. The first one is the crystalline effects. The preparation of high-quality indium-rich InGaN active layers in green LEDs is quite a challenge. 30% of indium needs to be incorporated in InGaN quantum wells to realize the green LEDs. This results in the formation of crystalline defects in three aspects. The first one is the weak chemical bond of indium to the nitride. The growth temperature of InGaN needs to be lowered to incorporate enough indium. The ideal growth temperature for PLGaN cladding layer is as high as 1000 degrees C to ensure low resistance, which induces serious thermal degradation of InGaN quantum wells. This latest mismatch between InGaN quantum wells and gallium nitride is as large as 3.3%. The second one is the quantum confined Stokes effect. A C-plane green LD suffers from this quantum confined Stokes effect (QCSE), which results into low luminescence efficiency. Some research groups successfully fabricated green LEDs with other than C-plane, for example nonpolar A-plane or M-plane, InGaN QWs free from QCSE, and semipolar R-plane InGaN QWs with small QCSE. The third one is the optical confinement. Since the refractive index depends on the wavelength, with increased wavelength, the refractive index difference between gallium nitride waveguide layer and argon cladding layer decreases. As a result, there will be a leakage into the substrate. The increasing thickness of argon substituting InGaN for gallium nitride as the waveguide both can be suppress the leakage of light. However, the latest mismatch will be aggravated at the same time. And the fourth one is the carrier leakage. With increasing of injection current, the slope efficiency of green LEDs was found to decrease. This phenomenon is attributed to the reduction of injection efficiency and induced by the carrier leakage. The electron blocking layer (ABL) has been employed to reduce this electron leakage successfully. Improvement of hole injection and electron overflow by a tapered argon electron blocking layer (EBL) in InGaN-based blue laser diodes. There are several obstacles that still impede the high performance of LDs. First one is suffering from a low hole injection efficiency because of the inefficient Mg doping in wide bandgap nitrides. The second one, the leakage of electron currents overflow can be very troublesome due to the low mobility of the hole in p-type 3 nitrides and the high threshold carrier density required for lasing. As a result, recombination of carriers outside of the active region reduces the quantum efficiency of lasers. So as a solution, a typical design of 20 nanometer aluminum O2 Ga gallium nitride O8 nitride electron blocking layer (EBL) was inserted between the active layer and the p-type layer of the light emitters. However, the solution had caused interface polarization charge problem. Yang and his team pointed out tapered three-layer algan EBL could improve the hole injection and electron overflow, but this is theoretically. He self-employed self-consistent Schrödinger-Poisson equation and transfer matrix method to study these carrier distribution and transfer properties. As a result, the tapered structure would eliminate the parasitic electron evasion layer and facilitate hole transport by letting more low-energy holes tunnel through. The suppression of electron overflow was achieved as the vertical electron current decreases to almost zero at the p side. Reduction of current threshold density from 2.0 kiloampere cm squared to 1.6 kiloampere cm squared and 15% of increased light output power were obtained. The second one is the improvement of GaN-based LZ diodes facets by FIV polishing. The nitride lasers have been fabricated with either reactive ion etching RIE etched facets or non-parallel cleaved facets. Both of these techniques resulted in a reduced reflectivity R because of its roughness and or non-parallel nature of facets. Gain and loss in diode lasers are determined by measuring the differential efficiency and threshold current density (JTH) as a function of the cavity length L, with R fixed at its theoretical value. This is based on the index difference at the semiconductor interface. This is made possible by reproduce atomically flat parallel facets provided by the cubic cleavage planes. The quality and reproducibility of cleaved GaN on sapphire using RIA techniques appears to be very poor. Therefore, it is difficult to know R and hence to determine the gain and loss of these devices. As a solution, Mac and his team introduced a new technique to prepare these GaN-based facets, which is the focus ion beam polishing. This will eliminate any scatter resulting from material non-uniformity, which is often rather large in the relatively immature nitride growth technology. As a result, the current threshold (ITH) reduced from 1.75 ampere to 1.08 ampere. The ND, as in the two-sided efficiency, increases from 1.3 to 2.5% as a result of the FIB phases preparation. So this is the LI curves taken before and after the polishing of RIE laser diodes. This is before and this is after. Suppression of optical field leakage in GaN-based green laser diode using graded indium in GaN lower waveguide. The optical field leakage to the gallium nitride substrate in GaN-based laser diodes green LDs can reduce the peak optical gain and weaken the outperformance of LDs. Fabrication of green laser diode it is harder than blue laser diode. This is because it is harder to incorporate enough indium into GaN to achieve this green laser. Spontaneous emission spectrum and the gain spectrum of indium GaN console wells will be broadened, hence results in the peak optical gain that is reduced. Piezoelectric charges will increase along with the increase of indium content when the LD structures are grown on C-plane sapphire or GaN substrates. This results in the weakening of the optical gain. Optical field leakage is a serious problem for the performance of the LDs, thus introduce additional optical losses or a parasitic ripple in the emission far field pattern. For a solution, a few solutions has been demonstrated before to overcome optical field leakage, such as using a thick ALGAN cladding layer, a thick and in-GaN waveguide, and also plasmonic GaN substrate. However, it is difficult to grow high-quality thick and ALGAN layer or a thick and in-GaN layer. Liang and his team developed a new way to suppress the optical leakage of gallium nitride in GaN-based green LEDs using a graded indium composition and in-GaN lower waveguide (GLWG). This figure shows the optical power versus the injected current curves of LD1 until LD4. The difference of these LDs is the LD1 is the cladding layer of 1 micron, 2 micron, 3 micron, and 4 micron. It can be seen that the output characteristics is improved obviously, and the optical power at 120 milliampere, and the threshold current is summarized here. For LD1 until LD4, the optical power at 120 is 78.44 milliwatts, 84 milliwatts, 100.89 milliwatts, and 103.38 milliwatts respectively. The threshold current is 60.15 56.56, 42.23, and 39.38 milliampere respectively. It means that optical power at 120 milliampere increases around 32%, and the threshold current decreases around 35% when the thickness of NCL increases from 1 to 4 micron. These results demonstrate that increasing the thickness of NCL can improve the output performance of GaN-based green LEDs by suppressing the optical field leakage. Thank you everyone, and have a good day.